you have been diligently watching this course till now, you would be now familiar with my usual spiel about how linearizing a problem is of great value. I repeatedly say that the central idea of this entire course is that nonlinear phenomena are difficult and linear phenomena are much easier. The derivative gives the best linear approximation, and now we are going to use this to actually solve a concrete problem that often pops up in the real world. In fact, I'm going to illustrate it with a commonly used algorithm for finding the square root, justify it using this linearizing idea. So this is really our first illustration of this idea, Newton's method. Newton's method abstractly is as follows. You have a function f from u to e, and we want to find x naught in u such that f of x naught is equal to 0. In other words, we want to find a 0 of a given function f. Okay, so the abstract Newton's method can be described in a few simple steps, which we are going to do now. We will just analyze a simple case in which Newton's method actually works, and we will prove that it works. Hubbard's textbook gives more information about Newton's method. Let me just say that Newton's method is till date not fully understood. We have only partial results, but for many practical purposes it's very useful. So here is the abstract Newton's method for solving this problem of finding a value point x naught such that f of x naught is 0. Start with a guess. Say a naught. Okay. So step 2 is if f of a naught is equal to 0, then we are done. Okay, but this is not going to happen in the real world. No one is that lucky. Now we know that if a naught is close to the solution, that is, if we have chosen a naught in such a way that it's not too far away from the actual solution, we know that f of x minus f of a naught is approximately equal to df at a naught times x minus x naught, where this x is supposed to be that hypothetical solution. Okay. Now third part, assume df at a naught is invertible. Okay. Then what you can do is you can pull this trick of taking df a naught to the other side. Okay, we can pull this trick of taking df a naught to the other side and set f of x to be 0. Of course, x is supposed to be the place where the solution is happening. So what we get is df a naught inverse f of a naught negative sign is nothing but x minus a naught, or in other words, x is equal to a naught minus df a naught inverse f of a naught. Okay, so what Newton's method says is start with an initial guess a naught, then what you do is you set a1 to be this quantity, a naught minus df a naught f a naught. Call that a1, then plug in a1 and see if f of a1 is sufficiently close to 0. In most practical purposes, you are not really interested in exact solution. You want something that's very close to the actual solution. That more than suffices. Check if f of a naught is very close to 0. Okay, of course it might happen that f of a naught is really small, but a naught is nowhere near the actual 0. That can happen. A function can get very close to 0 and then decide to change its mind and go in a different direction. That can happen. There's a real danger. All these intricacies have to be taken care of in a proper manner if you're going to use Newton's method in a crucial application like launching a rocket or something like that. In any case, you just iterate this procedure till you are sufficiently satisfied that you are close to a solution. So there is a theory behind Newton's method. You can prove a general theorem when Newton's method will work, but that is so far not the most ideal result. And this is the work of the Nobel Prize winning economist Kantrovich. I will not go into that in this particular video. It's not needed. It's done in great detail in Hubbard's book. Okay. All I want to do is to take a very special case and work out an example. The example is a classical one of taking square roots by this method called divide and average. Many calculators still continue to use this method for finding the square roots. So the example is as follows. We have b greater than 0, find square root of b. Find square root of b. Okay. So what we are going to do is naturally to apply Newton's method, we are going to consider the function f of x equal to x squared minus b and find a 0. This is the aim. Okay. So of course, what does Newton's method say? Guess a naught as the solution. Okay. Then what Newton's method says, because we are in the one variable setting, a1 would be just a naught minus f of a naught divided by f prime of a naught. Okay. So this is just Newton's method in one dimension. Of course, I am assuming that f prime of a naught is not 0. Anyway, for this function, the only 0 of the derivative happens at x equal to 0. I am never going to guess 0 as the required square root in any case. Okay. Now, we have the expression f to be x squared minus b. So, if you just substitute everything here, you get a1 is equal to a naught minus a naught squared minus b by 2a naught. Which is just half of a naught plus b by a naught. So this is the divide and average method. Okay. Start with an initial guess, divide b by a naught and take the average, and this is the better guess. Okay. The reason why this divide and average, this procedure gets you closer and closer to the root is the following intuitive idea. If you had guessed a naught to be very large, then b by a naught will be smaller than square root of b. So if a naught is very large compared to square root of b, then b by a naught will be smaller than square root of b, and this average will get us closer to square root of b because of that. Okay. So this is the basic intuition, but at least in this simple scenario, we can actually prove that repeatedly iterating this procedure, taking the next guess a2 to be half of a2 plus b by a2, half of a1 plus b by a1, and a3 to be half of a2 plus b by a2, so on and so forth, actually converges to square root of b. We can prove that rigorously. Let's see a proof. Okay. So we will first deal with the case. First assume that a naught is greater than square root of b. Okay. Then the claim is that square root of b is less than a1 is less than a naught, or in other words, the intuition behind this divide and average actually works. Okay. Now showing this is same as showing b is less than a1 squared is less than a naught squared. Okay, and here we can substitute for a1. A1 is nothing, a1 squared is nothing but 1 by 4 a naught plus b by a naught squared. Okay. Now let's just focus on the middle term. It expands out to a naught squared plus b squared by a naught squared. I should put a 4 here, plus a naught b by 2. So this is the not a naught b by 2, just b by 2. that a0 and a0 get cancelled out. So this is the expansion of the middle term. Okay, now what you do is multiply this entire inequalities that we want to show by 4. Okay, so ultimately what you want to show is 4b is less than 4a1 squared is less than 4a0 squared. Okay, so let's take 4 times the middle term, which is nothing but a0 squared plus b squared by a0 squared plus 2b. Okay, so we want to show that this quantity is greater than 4b. So what we do is we subtract by 4b. What you get is a0 squared plus b squared by a0 squared minus 2b. So this is after subtracting by 4b. And of course from elementary algebra, this is just a a0 minus b by a0 the whole squared, which we all know is going to be greater than 0. Okay, so this shows the one inequality. Okay, this shows one inequality. Now for the other inequality, suppose we have already b is less than a0 squared. Suppose b is less than a0 squared, then b squared by a0 squared is less than a0 squared. So what I have done is I have squared both sides and taken one a0 squared to the other side to get b squared by a0 squared is less than a0 squared. Okay, so this just means that a0 squared plus b squared by a0 squared plus 2b, this is just the middle term multiplied by 4. This is less than a0 squared plus a0 squared plus 2a0 squared. Okay, so I have just used repeatedly the fact that b is less than a0 squared and b squared by a0 squared is less than a0 squared, and this is less than 4a0 squared as required. So if you start with an initial guess a0 such that a0 squared is strictly greater than b, then it turns out that the one iteration of Newton's method gives you an a1 that's strictly greater than that's strictly greater than square root of b, but is less than a0. So a1 will be greater than square root of b, will be less than a0. Okay, so we have shown this, but this was under the assumption that a0 is greater than square root of b. How do you get rid of this assumption? Well, if a0 happens to be less than square root of b, then that means a0 squared is less than b. Okay, then observe that 4a0 squared is less than 4b, which is less than a0 squared plus 2b plus b squared by a0 squared, which is equal to 4 a1 squared. Okay, so how does this follow? Well, this follows because 0 is less than a0 minus b by a0 squared, which is a0 squared plus b squared by a0 squared minus 2b, and this shows that 2b is less than a0 squared plus b squared by a0 squared. Okay, so we have plugged this, that 2b is less than a naught squared plus b squared by a naught squared to in this equation here. We have just substituted. We have substituted here. Okay, so to put this in more concrete terms, what happens is a1 will be greater than a naught if a naught squared is less than b. Furthermore, a1 square will be greater than b. Okay, so what happens is, once you apply Newton's method with an initial guess less than square root of b, the first iteration, the next value a1 will be greater than square root of b. So we move on to the previous case. So we can safely assume our initial guess a naught was greater than square root of b, because anyway we will land up in this situation even if a1 was less than square root of b. Now because of this, we get a sequence an that is decreasing if we iteratively apply Newton's method. Okay, so what we are going to do is start with an initial guess, get an a1, start that as the new guess and keep repeating. Okay, because a decreasing sequence that is bounded below by square root of b has to have a limit, let a be the limit. Let a be the limit of an. Okay, now at each stage we had iterated by this procedure a of I plus 1 equal to half of ai plus b by ai. Then taking limits on both sides, you get a is equal to half of a plus b by a. Okay, this is just a fancy way of saying a squared equal to b. So the net upshot is, if you keep repeating this divide and average method, you will end up at the required square root of the number b. So this was a brief illustration of Newton's method. As always, Hubbard's book gives this in great detail. Then in the appendix, the entire proof of Cantor-Wich's theorem is there, and the proof of the inverse function theorem using Cantor-Wich's theorem is also present in Hubbard's book. We will use the Banach fixed point theorem to prove the inverse function theorem. However, some parts of the proof will be inspired by Newton's method, though we will not use Newton's method in a direct way. This is a course on real analysis, and you have just watched the video on Newton's method.